So today's topic is an identification of clay minerals. In identification of clay minerals, there are two types are there. That is, one is the physical methods of identification. Another one is called chemical methods for identification. So what are these and what are the types are there? What is their role? How we are going to identify? And mostly very first interesting topic is called X-ray diffraction. Very useful. This is the way we can use the sample again and again. If you go for this type of analysis, we can use the sample again and again. It's a non-destructive method. Another one is called electron diffraction studies. Using some electrons and another one is called electron microscopy. The image, I think in Google, if you search some any images for the clay minerals, you will get this electron microscopy images. At layer we can see. And DTA. DTA is nothing but differential thermal analysis. Differential thermal analysis. That is a differential thermal analysis. And another one is called surface area. So based on surface area, naturally, whenever we study about any mineralogical subject, we always study what is the surface area of so-called mineral and what is the surface area of another mineral. Like that, we can identify. So these are the major methods and physical methods. These are the physical methods. These are all X-ray diffraction method, electron diffraction studies, and electron microscopy, differential thermal analysis, and surface area. Coming to the chemical methods, we can say CEC, cation exchange capacity, we can see that, and molar ratio, potassium determination, and Y index, some electrometric properties. So like this, we can see what are the different methods of identification of clay minerals. Now we will follow the further slides will be continued like this. Very first one, students, the very first we will see the differential thermal analysis. So it's the destructive analysis, students. So differential thermal analysis is complete destructive analysis. The destructive analysis means the sample we can't use. Once we use the sample, we have to destroy that sample. We can't reuse the sample again, which is quite opposite in X-ray diffraction. Mostly in thermal analysis, a material is heated, its structural and chemical composition undergo such changes such as fusion, melting, crystallization, oxidation, decomposition, and transition, expansion, stirring, etc. So all these conditions will be happen. So using this thermal analysis, such changes can be monitored even at of our interest of atmospheric pressure. The obtained information is very useful for both quality control and problem solving. So this type of analysis, we will go for some thermal heating, and we will see what kind of changes were happening in our in present given respective pressure and temperature or present atmosphere. And this type of analysis is very useful for both quality control. We can see how much quality is there, quality of mineral we can judge, and also is there any other problem is there, we can judge that problem also. So now we will see very in detail regarding the thermal analysis. What are those conditions? So methods based on thermal properties. So completely, as I said that here we will see some thermal changes. So what are those? Very first, differential thermal analysis. See, students, is nothing but just comparing with the inert reference. See this, read this line. Temperature difference between sample and inert reference material. So this is what differential thermal is equal to sample by reference is measured as both are subjected to the identical heat treatment. That means we will take one sample of our interest and we will go for reference sample. Reference sample means we know the properties of that particular sample. We know the particular sample. So we will heat our sample, the unknown sample, the collected from the soil, and the reference sample. Reference sample means we know all the properties. At how much temperature it will go for melting, at how much temperature to go for other chemical reactions, everything. We will have proper knowledge on this. So we will compare. So for up to 1000 degrees, how much, what are the changes happening between them. So by comparing with the reference sample, we can identify what kind of mineral is there, what kind of clay minerals is there. Another one is called differential scanning calorimetry. Here also the same thing will happening. Either sample and reference is maintained at same temperature, even during a thermal event in the sample. That means that changes. So what will happen here? After when we heat it up to we take the sample to a certain range of temperatures, and the amount of energy required to maintain zero temperature between the difference between the right. So regarding with the thermal analysis, differential scanning calorimetry, you will see the after heating, after taking the sample and reference to after certain thermal event, that means certain temperatures, what we will do? We will calculate the energy required. So how much energy required to maintain zero temperature between the sample and the reference will be calculated. This is a formula for that. Have a small d dq by dt. This is a sample. So difference how much energy is required to maintain the zero. How much calorimetric energy is required zero will be calculated. That is called the differential scanning calorimetry. Another one is called thermogravimetry analysis or methods, TGA, that's thermogravimetric analysis. Here we will heat the temperature and we will see how much mass is being lost by the sample. Is a thermal just quite similar to our gravimetric analysis in our regular chemical analysis. This thermogravimetric analysis. That means so thermogravimetric analysis means the change in mass of the sample on heating is measured. So on heating, definitely there will be some loss of mass in the sample. So we will calculate how much mass is being lost by that particular sample, and we will check the difference in the mass. So this is called the thermogravimetric analysis. So these are the three different analysis. One is called differential thermal analysis, differential scanning calorimetry. That means how much energy is required to maintain the zero temperature. It's called DSC, that's called differential scanning calorimetry. Another one is called DGA, that's called thermogravimetric analysis. That means how much mass is being lost by the particular sample is being calculated in this type of analysis. So these are the analysis. These are thermal properties. So now coming to our original theme, that's called differential thermal analysis. So mostly this type of experiment or this type of analysis is very useful for both crystalline and amorphous material also, which is very important. Even we can identify the amorphous material in this type of analysis, but which is not possible in X-ray diffraction analysis. So what will happen means here we'll put our unknown sample. We will put in the instrument we use our unknown sample and the reference sample also, and we heat it both the samples side by side from 0 to 1000 degrees Celsius. Okay, students. So that, as I said before, the reference material is a standard material. It's not normal. It will be thermally inert, and we know what is peculiar characteristics. So now we will see a number of compounds have been used. So for this reference material, there are many compounds like Al2O3, aluminum oxides, and calcinated kyanite. We have used calcinated kyanite. So these are the few inert components has been used. So the heat was controlled uniformly and steady rate through the analysis. The heat will be just we can't go through or he give the heat in a very random way. We will increase it steady by step, slow by process. Then only we will give the particular heat analysis. We will heat the sample in a very steady rate. So mostly this heating range will start from 0.1 degree Celsius to 2000 centigrade Celsius per minute. So naturally heating mostly, what is the rate of heating? It will be around, mostly for the most of the purpose mostly we can go up to 20 degrees per minute. For 20 degrees per minute also is used. So what will happen during this heating process? Unknown sample undergo some thermal reactions. That is what happening. If any substance go on heating in a particular given at known temperature, definitely there will be some transformation. There will be some changes will be there. So these changes, so the difference in changes between the unknown and reference sample, we will plot one graph. So by comparing our reference sample, the so-called reference and our unknown sample. Unknown sample means our soil sample, our unknown sample. So we will heat the samples at this temperature, the so-called temperature from 0.1 to 2000 degrees Celsius and 20 degrees Celsius. So we'll go for thermal reactions, and we'll plotted one graph. How that graph will be look, sir? It will be look like this. So I will show that graph. So generally that graph has the two types of peaks. One is called the endothermic peak, and the one is called the exothermic peak. So this is endothermic peak, exothermic peak. So what is this endothermic and exothermic peak? So it is nothing but, read this line. If the temperature of an unknown sample, the sample which we collected, becomes lower than the reference sample, delta T is negative. That means, say for example, this is a baseline. So this is our sample. So if our sample was, so we heated our sample. That sample, our collected sample was very less in temperature. So the graph will be lower than the reference sample. This is a reference sample temperature, but our sample was very low, undergo very less temperature changes than our reference sample. So the peak will be downward. This is called the endothermic peak. But it's quite reference. When the temperature of our known sample was very high than the reference sample, the delta T will be here in negative, but here in an exothermic peak, the delta T will be in a positive. That means it is quite opposite. So it will show the upward peak development. That is called the exothermic peak. Mostly, if the delta T, if the delta T, the temperature difference, this is called delta T, students. This is called delta T. If the delta T is zero, there is no difference. That means it was following this baseline. What will happen? There is no change. Means between the unknown and reference sample, it is considered the baseline, and it will be it will be a straight line purpose. So if it is low, means it will go downward. If it is high, means it will go upward. But if there is no any temperature, if there is no any temperature difference, means what will happen? It will be only in a straight line. It will follow the baseline. Better, I will show the original graph which are included in this PPT. So the mostly this curvatures with peak serves as a fingerprint. Yes, this curvature, these graphs, the so-called graphs will be serves as a fingerprint that will use at a specific temperature at which the peak develops as diagnostic for the identification of minerals. Generally, these graphs will give a proper information. Generally, it will be considered as a fingerprint for the particular mineral. So generally, differential thermal can be performed with a liquid or solid samples. We can use both liquid sample and solid sample. When the soil samples are whole, with the soil sample, whole soil, sand, silt, or clay fractions can be used. So we can use any type of sample we can use. We can use whole soil sample, or we can take sand separate, silt separate, or even we can take the clay fractions also we can take for the differential thermal analysis. So naturally, when the whole soil sample were analyzed, there is less than 2 millimeter fraction should be treated with 30% H2O2 to remove the organic matter, which may interfere, giving a strong exothermic reactions. So students, we use this H2O. What is H2O2? What is it?
Hydrogen peroxide.
Hydrogen peroxide. Where we use hydrogen peroxide in our regular soil?
Organic matter decomposed.
Which experiment we use? Other than this differential thermal analysis, we use in another experiment also. What is that?
Organ.
Organic carbon estimation.
Uh, no. There is one experiment. We use H2O2. What is that? In that experiment also, we destroy the organic matter.
Textural analysis. Soil textural analysis.
Finally, you got it. It's the soil texture analysis we use. Actually, there are two types of texture analysis. One is international pipette method and hydroscopic method. In Coimbatore, mostly they follows international pipette method. In that, there they use this H2O2. H2O to destroy the organic matter. Why they use H2O2 in that texture analysis? Can anyone answer? Why they use H2O to destroy the organic matter? Any reason is there? Illiteracy, don't answer. You have full subject. Can anyone answer? Other than illiteracy and Mr. Adam, you also don't answer. You both are in subjective. So any others like Subhash, you can answer. Vedavyas, we can also answer. And my favorite NRS in the student, you should answer.
No, sir.
No, actually, while we are doing texture analysis, we should, organic matter will act as a binding agent between the particles, right? It will act as a binding agent. So while doing texture, so like this, we destroy the organic matter content by using H2O2 to remove the organic matter. So if this organic matter present in the sample, what will happen? It will give a strong exothermic reactions. Because organic matter also with the temperature variation, organic matter also will be added to the peak. What will happen? The peak will be shown very high. If it is show like this, you will get a wrong data analysis. To avoid this, we use H2O. So in general analysis, whole soil gives a only peak of low intensity. Same peaks are very large and intensity. So these are all practical way of things. So this is regarding. I will show that original graph of ETA. Yeah, this is what student. This is what I need to explain. So when your temperature was more than the sample, your non-sample temperature was more than the reference sample. This is called the reference line. If it is more than, your peak will be goes up. The delta T will be in positive. The temperature variation will be in positive. It is called the exothermic reactions. If it is less than the baseline, that is delta T, it is called the endothermic reaction. So this is the variation, students. So here the delta T is a negative, it is delta T is a positive. So if in case, if in case there is no changes, it will follow the baseline. It will follow the baseline, and it produce only straight line. The graph will be in a straight line. There will be no change. So these are the graphs regarding the thermal analysis. So what is this endothermic and exothermic reactions? Nothing is there, but we will read about it. The thermal reactions contribute changes in temperature of the sample. Generally, dehydration, removal of water, dehydroxylation, fusion, evaporation, sublimation yields to the endothermic reactions. So here the dehydration, dehydroxylation, fusion, evaporation, and sublimation yields to the endothermic reactions. On the other hand, oxidation, crystalline structure formation, some decomposition reactions comes under the exothermic reactions. So these are the few type of reactions which involve in the endothermic and exothermic reactions. Now we will see about what is happening. So, say continuing the what are the advantages of the DTA, that is differential thermal analysis. Instrument can be used at very high temperature, so there is no problem with the instrument, because generally in soil science instruments will be very sensitive. We should take very much care about our sensitivity of the instrument. But in this instrument there is no problem. We can go for very high temperatures. Even though we can maintain at high temperature, the instrument will be very sensitive. We will get a very paka analysis. Characteristic transition and reaction temperatures can be accurately determined. So determining of the particular analysis was very accurate. But what is the disadvantage? There is some sort of uncertainty. There is some sort of confusion of in between the fusion transition reaction. Estimated there is a chance of 20 to 50% of chances. There is some uncertainty in heat. If there is any problem in the heat supplying of heat, means definitely we will get some wrong result. We won't get any proper or paka analysis. This is only disadvantage in the differential thermal analysis. Now we will see another step what is happening. So this is regarding differential thermal analysis. I hope you have to keep only few things. What is exothermic peak? What is endothermic peak? And it is a destructive analysis. We can't use sample again and again once we use, and this type of analysis is completely used for both crystalline structures, the so-called crystalline structures and amorphous structures. Both we can use this differential thermal analysis. And there are many type of differential calorimetric analysis I have already shown. Just we will brush up all the this one. Differential thermal, differential scanning calorimetry, and thermogravimetric analysis. So these are the three type of analysis we have learned. So these are the important things you have to remember in DTA, that is differential thermal analysis. Now we will see the X-ray diffraction analysis. This is very good, very nice. This is also one of the excellent unique technique used in the identification of clay minerals, and it gives a qualitative analysis. It will give a very qualitative, but it is a quantitative. But it is a qualitative analysis. How good was material is there? It is a non-destructive method, meaning sample we can use for again and again. So once we use any sample we have used for this X-ray diffraction, we can use the sample for another analysis also. So we can use this non-destructive analysis. However, the method is not the major disadvantage of this type of analysis is it can't be used for amorphous and non-crystalline structure. Can anyone answer why? Can anyone answer why we can't use this application? Loresi and Adam, please, both of you don't answer. Let your friends to be answered. Can anyone answer?
No crystal structure in amorphous minerals.
Okay. There will be no crystalline structure amorphous. Okay, I know that. So what is the relation between
there is no X-ray diffraction in amorphous.
Good. Use that word. Good. That is X-ray diffraction. So then naturally, if there is no proper arrangement of ions or everything, it will be a big problem. So that's why we can't use this X-rays in amorphous and non-crystalline minerals, because there is no proper arrangement of clay lattice. So now coming to this, based on the base of use X-ray diffraction is a systematic. What is the base for this? What is the base for this X-ray diffraction analysis? It is completely systematic arrangement of atoms and ions in the crystal planes. So this is the major fundamental base for this analysis. This arrangement, whatever the X-rays was spread on these atoms or ions, they will reflect a definite intensity of X-rays. So we will calculate. So this is the base. So each material species is characterized with specific atomic arrangement. We have learned all these things regarding the what is a crystalline unit, what is a clay unit, what is a body centered, paste centered. We learned many things in our previous videos. If anybody have not attend that class, please go through. I have provided the link. Please go and see that video for once about this specific arrangement of atoms and creating. My God, there's no power. Okay, creating characteristic atomic planes. So right, each material has specific atomic arrangement, creating characteristic atomic planes that can be diffract. Diffract means reflect the X-rays. So this characteristic planes, that means arrange that planes. We have learned that that arrangement of that layers, crystal layers, like what is that? Silica tetrahedra, aluminum octahedra, 1:1, 2:1, 2:2, 1:1. We have learned many things now. So that specific arrangement of atoms will be read by these X-rays. So in most of the crystalline, the atomic spacing or crystalline planes are almost same dimensions as the wavelength of rays. So almost the wave nature and dimensions of the crystal planes will be same. That's why we can use this X-rays. Very first students, Lev, a great scientist. This person have first identified this. Can be used this X-rays for our identification. We can identify with this person 1912. So the diffraction pattern mostly used for fingerprint of identification of minerals. So this diffraction pattern, so the so-called diffracted pattern, will use as a fingerprint for the identification of mineral species. So this is regarding X-ray diffraction also. But we will go very in depth. What is this X-ray? So generally, students, how these X-rays are produced? Very elementary. We have how we usually learn +2 question. Generally, we will use some fast moving electron hitting a metal target. By hitting a fast moving electrons, by hitting a metal target, what will actually, do you know why this X-rays, the name X-ray? Let's start. Anyhow, so general X-rays are produced by hitting a metal target. What will the X-rays is produced? So mostly the excited atoms will be wavelength will be around 0.1 to 100 angstroms. Generally, there are two types of X-rays where X-rays will become or radiation will come. We want only one type, so we will block the beta rays with some blocking agents like copper. We will block some nickel filters and we release only alpha rays. So we use this one type of rays. We won't use both. We won't, because if we use both, we won't get proper analysis. So we use only one type of rays. Alpha rays we use for isolation for the use of analysis. So this beam of copper alpha rays radiation hit the crystalline surface, which X-rays are scattered. So these rays were used for our mineral matter. So it will be scattered by the atoms of the crystalline. This scattered X-rays become quantitative. So this scatters with this scattering experiment is the only when the particular X-ray, this so-called copper alpha particles, potassium alpha particles have been released. So this will be hit in the mineral surface. The mineral surface means our unknown sample. So the rays will be reflected. Those rays will be considered only quantitative only when it obeys the Bragg's law. So only when those particular rays. So for example, this is a sample, and I'm hitting with some X-rays. So it will also will be there will be some reflections. So this reflection, these resultant rays will be quantitative only when it obeys this law, Bragg's law. So based on only this rays will be a quantitative only with obeys the Bragg's law. What is the formula for Bragg's law? It is n lambda is equal to 2d sine theta. Now we see what is the d? It is the d spacing between the atomic planes. The d is nothing but spacing between the. I have said what is the d spacing in the mineralogy class. What is the d spacing? Can anybody answer? What is the d spacing? Yeah. So this is the Bragg's law. This is n lambda is equal to 2d sine theta, where d is the space between the atomic planes, and lambda is nothing but wavelength, theta is nothing but angle of diffraction, and is nothing but order of diffraction. And what is this Bragg's law, sir? What is this formula? We will see in next slide about this Bragg's law. So this is the regarding the Bragg's law. This is the Bragg's law. Bragg's was stated like this. When a crystal, this is the law, students, we should be right as such. When a crystal is bombarded, that means hit with X-rays of a fixed wavelength, similar spacing of crystalline lattice in bracket at a certain angle. So we are bombarding, that means hitting the X-rays with a fixed wavelength at a certain angle. Intense X-rays are produced, reflected. Intense X-rays are produced when the wavelength of scattered X-rays interfere constructively. So reflect X-rays will be produced when the wavelength of a scattered X-rays will be produced. At that interference surface, some scattered, some reflected rays were produced. When this constructive interference occurs, so that interference occurs, the diffracted beam of X-rays will leave the certain angle equal to the hidden beam. I will show the image in next slide. Just read this line. When the constructive interference occurs, when the proper interference, constructive interference occurred, a different beam of X-rays will leave a certain angle equal to the top incident beam. To the top incident beam. What are those? We will see. This is what the explanation for that. So predict that all planes have certain crystal have dioxide, which is the inclined angles of certain incident beam. The angle is theta depend upon the wavelength. So whatever the incident rays was spread in angle, that angle should be equal to the diffracted rays. This is what the Bragg's law. So how much intensity you have been released, the angle between these two in diffracted incident rays should be equal. This is what the Bragg's law says. This here you can see the incidented beam, that is A, B, C has traveled several wavelengths further that incidented of the A, B, C. Diffracted from suction equal atomic yields to different diffraction max. That means whatever the incident rays should be equal to the diffraction rays. The angle of incidence should be equal in both diffracted beams. This is regarding the atomic Bragg's law. This is regarding the Bragg. I hope you're getting my point. What I'm explaining regarding with the Bragg's law. So the data, mostly this angle is completely depend upon the wavelength. So how much the depend upon the wavelength of X-rays. So how much wavelength we have used it. That is completely, this angle is completely depend upon the wavelength. And d-spacing is called the d-spacing between the two layers is called the crystal lattice, between two crystal lattice, the d-spacing. So this is regarding the Bragg's law. Only your so-called diffracted rays will be quantitative only when it affects this Bragg's law. We'll see next about the diffraction law. Same thing I have explained here. Incident, these are the incident rays, these are the scattered rays. So all angles should be equal. All the angles should be, incident angle should be very equal. Same thing. What I have explained, just I put in a pictorial representation. This is for your preparation purpose. Same thing. This is also repeated arrangement. The kind of arrangement of crystal atoms of each atom is scattering the points. Generally, what kind of arrangement is there? What kind of layer lattice was present completely read by this incident and reflected X-rays. Very much so. Okay, very good, very nice. But for doing this analysis, we need to prepare a sample for analysis. So just like differential thermal analysis, we can't use whole sample. Here we have to treat the sample. We have to prepare the sample to hold those X-rays rods. So what are those? Very first, we have to use we use ethylene glycol or glycerol, which replaces the water, give a constant interlayer spacing. So generally to replace water, we use glycerol or glycol, which gives a very constant interlayer. So when this water was replaced, the layers will be very constant, will give a very perfect X-rays we can use in a very perfect manner. At the same time, baking at the various high temperatures to destroy the parts of crystalline structure. Generally, this baking is used generally to get the proper rays, proper studies. They will bake the temperature, some high temperature, which very slightly will be destroyed. Not we should not completely we should not destroy. That this we need some very skill to do this type of practice. And another experiment, another method including that saturation with cations. So generally we saturate here also to replace all this water molecule, etc. We'll saturate with magnesium or potassium. We produce some diagnostic structural changes. So by using this magnesium potassium also we will treat the sample to get the proper diagnostic surface. But here also we'll get some sort of problems will be there. But we know what type of cation we use it for that particular sample. So these are the few methods which we use for the clay preparation analysis. Sample preparation analysis, generally we go for diffraction and prepare the random powder sample. We should use powder sample. Unlike differential thermal analysis, we can't use whole sample. We use for powder sample as oriented sample, and with the aid of glycol, clay sample is made into paste. That means to replace the water molecule, we will make into paste and roll it in a rod. Actually, if anybody have experience in this X-ray diffraction, means they will load this sample into the rod of 0.3 to 0.5 mm thickness, This powder sample can also be prepared by pushing a paste into the specially designed wedge holders. That means that the holding, there are some few holders, it will wedge holders, they will use this and we will push the samples. So a currently most popular method mounting X-ray sample is prepared by orienting of small microscopic glass slides. Present, we are using microscopic glass slides or porous ceramic plates have been used. We are using a glycerol means why? Because to avoid some problem with water molecules. We use glycerol. Sometimes, as I said, sometimes we use for saturate. We can saturate the sample with potassium and magnesium ions also. So another one is called clay suspension is made properly and pipette into the slide. Approximately 15 to 25 milligrams of clay in transparent for 100 centimeters per square. So when we use this glass slides, we should get at least 25 milligrams. So 15 25 milligram sample should be there. That should be present around 10 centimeters square. The sample should be present between the 10 centimeters square area. It should be present. So after sample is allowed to dry, after treating all the sample, we should allow to dry at a room temperature. It is ready for analysis with a direct recording and X-ray spectrometer with X-ray pattern printing charts with it. So generally, what after treating the glycerol, after treating the sample with glycerol, after doing all this experiment, after allowing to dry at the area of 10 centimeters square, we'll dry it and we put it under the X-ray spectrometer. And after for some time, it take long time, students, which is not unlike the differential thermal analysis. Here in X-ray diffraction, it will take a long time for getting a printed chart. So after when we get nowadays everything is got a computerized. So after a few minutes, few hours, minutes to hours, take very lengthy time. So at that time we will get a printed charts. We will get the printed charts. So this is the what, student. After getting all these things, we will get one graph like this. We get one graph like this. These are the counts per second. How much X-rays was used. This is the theta. This is a unit. So for each and every peak is represented the 1 minerals, 7.15 minerals, all those things. These are some sort of graph. Actually, to get no need to go what in detail about this graph. If you, there's a different that will be very different. You will learn when you work with this X-ray diffraction only came to know about this graph. So another experiment called electron diffraction studies. It's quite similar. Quite similar. It's a fast electron means fast electron with a lower penetration energy than the X-ray. It is almost quite similar to the X-ray diffraction. The only thing is that here the efficiency is very more than the X-rays. These electrons will penetrate at very low energy, but when compared to X-rays. So and desirable basal spacing, clay spacing has been recorded. So naturally, in this electron diffraction, we use the basal spacing calculation also. This is quite similar. The electron diffraction is nothing but in here we use X-rays. Here we are using fast moving electrons. There is only difference. So if we compare with the X-rays, what is so both are same, sir? Why we should use this one? There is some advantages than the X-ray diffraction. Exposure time maybe few seconds to compare with few hours in X-rays. Just now I said it will take some few seconds to few hours in X-rays. Electron beam fail to produce penetrate beyond the surface and scan to the X-rays too. So another advantage, the electron beam is to penetrate beyond the surface. It will go very in deep. The electrons can go throughout the sample, but X-rays can't go beyond that one. So there is some this is the advantage over the X-rays. So we can save the time and we can analyze very properly when compared with X-ray diffraction. We can use this electron diffraction studies very effectively. So another important experiment is called electron microscopy. Quite similar. Here, electron microscopy usually we nowadays is very famous. We getting images. We use electron microscope. Here also we will use electron beam. Use it for study the shape, size of the particles. Naturally, whatever we so-called electron images all coming from here only. Due to the negative charge of the electron beam have one advantage over the X-ray diffraction. Due to the negative charge is there for the electrons. By using these advantages, we can prepare the very microscopic image of our clay membrane. Usually we see mostly like plate like kylets, so we can see what is the arrangement of kylet and monomolar light very clearly in electron microscope. And lathe shape like non-ternate and halocyte. So lathe shape, plate like shape, all the shape we can get the shape also. Even but in X-rays or electron that another after that electron fast moving electron method also, there we can see only some quantity, but here we can read what is the shape, what are the layers arrangement, everything we can see very clearly. So method analysis, so how we have to do this? In this method, a drop of dispersed clay suspension is used. We have to use waste on a specimen supported on a plastic film. And examining after showing after a shadow casting. Shadow casting means just shadow casting, generally we use in microbiology. Just we will tilt the slide to shadow cast to provide a sharper contrast grading. So to just spreading, just spreading, and by doing all this thing, we will get a better 3D information about the particular surface and well thickness. This is a better. This is what, students, we will get a 3D images. We will know the shape, what is the arrangement, everything we can read from this electron microscope. So this is what I'm saying. These are electroscopic images. We can see what the shape is there. This is the ellite 1:1 type. This is 1:1 type. So this is the ellite. This is 71 micrometer range. This is, and this is a Montemore light. We can see Montemore light is a 2:1. We can see some gaps between the layers. You can see the between the layers there. Here we can see some. These are the layers. We can see layer shape. This is the halocyte. We can halocyte completely. You can see what the shape is present in. We can see the 3D images. And Tamplug light, it is another one, and like this. So these are the few images. Coming to another one is called molar ratio. Silica oxides. This is nothing but just comparing the silica oxides with other oxides. Mostly, this ratio between silica oxides and other oxides is generally 2.4 for Montemolar dominated clay. If it is less than 2.4 for Kylenet dominated clay fraction. So R2 remains the sum of it is nothing but the other sesquio oxides means what are those? Is iron and aluminum oxide. Just comparing what ratio between silica oxides and other iron and aluminum oxides. This R2 is represented iron and aluminum oxides. This is just comparing. It's a molar ratio. How much ratio is there? We can compare it. So another important is called specific surface area. It is inversely proportional to the particles as depend upon the colloidal nature of the clay. From past day one class, I'm always explaining what is the specific surface area. As the particles has decreases, specific surface area will be increases. So this can be determined experimentally retaining by the ethanol glycol. We have to treat this ethanol glycol on the surface, and the value obtained compared with the pure clay mineral. So after treating all the specific surface by calculating specific surface area, we can obtain the standard pure clay water. So based on specific surface area, internal surface area, molar ratio, these are the few methods which is used. And so these are the ranges we used by using ethanol glycol retention. Is the internal surface area, external surface area, total surface area. What is internal surface area? What is external surface area? I have given the explanation in my last video. Internal surface is nothing but surface area between the layers. External surface is nothing but the edges, surface part. It's called the external surface area. So these are the surface area, etc. So I don't want to read all these things. No, naturally, Montemole has a very specifics are very high. Sorry, not Montemole. Vermiculite has a very high specific surface area, and followed by the Montemole, and very less is Kylenet. Please, that is what this is regarding the Kylenet, Illite, Montemolate, and Muscovite, Montemole, Chlorite, and Vermiculite. This is regarding so large surface area play imparted some properties. So due to the if you have a very large surface area, there will be peculiar characters will be there. What are those? Swelling, shrinking, viscosity, and sedimentations we can see in the water. So these are the some and have some colloidal nature also. We can get some colloidal nature properties also. This is regarding the surface area. Coming to the next is called electrometric properties. Almost we now gone through. We came to chemical analysis. It's called this include the potentiometric and conductometric titrations. Conductivity, potentiometry. We usually read in this chemistry part, conductometry, all these things. So this is due fact that soil clays retain homoionic. They are homoionic because all are negative. Generally, cations will be observed. With a single cation that will satisfy the charge enter cation exchange capacity. Nothing homoionic means the clay surface negatively charged. Generally, it will attach with positive charge. Called homoionic. This is one type of ion will be there. Anyhow, this is due to the fact that soil clays retain homoionic with respect to the single cation that satisfy the entire cation exchange capacities. So that the titration of clay gives the information about the exchange capacity and natural properties of the clay. Nothing but our CEC, what the so-called CEC, we calculate now all those things. So those are called some electrometric. Our C is electrometric property, and our EC also the electrometric property, pH, and all this comes under the electrometric properties. Coming to the potassium determinant. So micaceous clay mineral like illite, muscovite, biotite, and inferred from potassium oxide. So all these are potassium derived minerals. So muscovite, So how much potassium? So the amount of potassium is determined. So based on the potassium determined also, we can identify the clay minerals. Example, your moscovite biotite, like potassium 9.4 percentage and 10.4 percentage in moscovite. For illites, it's around ranges from 6 to 10 percentage. Chlorides and vermiculite minerals indicated by the magnesium oxide content also. So all this, so there is nothing but the mineral based on the mineral, potassium mineral, we can identify the what kind of potassium is there. Another one is called Y index. Y index is actually this index is one mathematical model proposed by the Martin and Russell. This index was combination of potassium content and ethanol glycol retention by the internal surface area and C's. It is nothing but, students, this Y index is nothing but it is a combination of the potassium content, ethylene glycol retention. So by internal surface, we will treat the sample with the EG solution or ethanol glycol solution, and by the internal surface, naturally the internal surface can generally see. So by combination of all these four, we will get the what is Y index. So by multiplying all these, by combining all these things, we will get one value. That is that form. They have given one formula. Y index is Martin and Russell is nothing but 1 by 3 A into 10 into B into 10 into 6 20 25. What is this? Is like a potassium content, ethanol glycol internal surface area. All comes under here. So here A is presented for the potassium content, B is contained in the internal surface area, and C is the CEC. So by combining all these things, we will get some values. So some index will get. So the A is nothing but your potassium content, B is your retention content, and EG so the ethylene glycol solution, C is nothing but your CEC, cation exchange capacity, P plus per kg. So why have this both people have done some mathematical? This is one type of mathematical model for the identifying of clay mineral. It's called the Y index. Now we will see what are those conditions. If the value of Y index is between 0.5 to 0 to 5, that is mostly in this range we can get the kaolin type of clay mineral. If it is 5 to 25, it is called the illite type. If it is 25% and more, that is comes under the monochrome. This is called the Y index. This is completely mathematical model, students. So 0.0 to 5 kaolin type, 5 to 25 is the illite type, 25 or more, it's called the monochrome type. Now we will see the another one. Another one, finally we come at the elemental chemical analysis. So based on chemical analysis to find out the nature and dominant of the clay in soils, to find out the elemental composition. So what is the percentage, and also total percentage would be approximately 100. So we will find out the chemical. By finding out a chemical combination also, we can find out what type of clay minerals are there. So this is regarding the chemical analysis. Chemical analysis is nothing but we will see what type of, how much, what is the composition present in that particular sample. So finally we are what type of conclusion I want to give means soil clays being essentially is a mixture. Soil is very dynamic. The different properties will be the mixture of clay suitable combine of these methods. So we should not restrict to only one kind of method. We have to use all type of method which is chosen for identifying not only dominant in mineral but also other less abundant clay fraction also. That means we can have some, we should not focus only on one type of analysis. We have to go for other type of analysis. We have to go for other diffraction analysis. So a set of analysis are suitable for our analysis should be used. This is overall for today's class. My conclusion is like this. With this, and thank you very much. And 1 minute. With this, I'm concluding my class.